Today we continue our lecture on link state routing with the topic that is not strictly related to link state routing and is called software-defined networking. We have seen a number of methods that can be used to automatically compute routes in networks with focus on link state routing. Those methods can and often are complemented with centralized operations on the routes that are computed. Let me motivate this with an example. This example which is taken from a paper that I'm citing here, is when an operator has observed that some traffic has become very important in volume, the red traffic. Operators monitor the amount of traffic that is occurring in the network. That's called anomaly detection, because any open network is subject to attacks of all kinds. So this network has noticed that there is a large volume of red traffic, an abnormally large volume of red traffic, which might be simply business as usual. There's a very popular content somewhere, but it might also be an attack. So in order to know exactly what happens, networks use deep packet inspection devices, called here a scrubber. Those are computers or farms of computers that will look deep inside the packets. Of course, this is very expensive. That costs a lot of computing power, and that delays considerably the traffic if you would apply to all traffic. So we don't do this to all packets, but if there's a suspicion here, you would do it to the red flow, except the infrastructure that does this packet inspection is perhaps localized here between routers B and C. So what you would like to be able to do is to divert some flows to some specific location. In this case, you would like that the red flows are diverted to the scrubber that lies between B and C, but only the red flows, not the blue flows. The blue flows were noticed to be business as usual, so there's no reason to submit them to this quality of service degradation that the scrubber will impose. How do we implement this? Well, a solution for that is to use what is called software-defined networking, which consists in implementing in routers exceptions, which are called per flow forwarding rules. Normally, a router performs longest prefix match based on the destination address, but you can add to a router more specific rules that would say when a packet has to be forwarded, you first look whether there is an exception rule that applies to this packet. So you look for a rule match in the list of rules. This list might be, there might be more than one rule that matches a given flow. So there is typically priorities in this list, and you look for the rule with highest priority that matches here. If there is no rule match, then you do as you would normally do. You go to the IP forwarding table and do longest prefix match. So this is used in routers. This is also used in switches, where in switches, in principle, we have, instead of an IP forwarding table, we have a MAC destination address table, where we have an exhaustive list of all the MAC addresses that are known in our network. The same can apply here. Instead of using those matches in the MAC address table, you can apply one of the rules here. Let's see on an example what this could mean. This is the same example we saw when I explained how IP packet forwarding works. So these are the IP forwarding tables. They're called the routing tables in routers. You're familiar with that now with the labs. And this is the routing tables as they are configured in this small network. Assume that in R1, in addition to that, we add a flow table that is containing two lines here. A flow table is a row in a flow table is a description of the flow of the action and the priority. Higher priority means precedence. So here we have a first rule that says it applies to the flow that matches this pattern. So flow spec, depending on the system, can be based on any grammar. Here, typically, it's input an input port and source and destination addresses here. So here it means any flow that comes on input 0 on this interface of the router that has a destination address that matches the string b.d.anything. Then for such flows, for any packet that matches this description, the action is output to port number 2. So we will send it to port number 2. Whatever the routing decision of the routing table says, we will do that before. So this packet will be sent to output number 2. And this has priority 50. Another flow specification is anything that has destination address b.d.star. So it's a subset of this one. The action is drop. We kill this packet. So those are the two rules we have here. Actions are here output, drop. You can imagine other actions. Actions may be output, drop. Sometimes they can be also replicate. This is one way of simulating multicast, for example. There can be other type of actions that you can imagine. So let's assume we have this configuration in router R1. What will happen to a packet from Lisa and from Homer to the enterprise server? So Lisa is this host, Homer is this one, and the enterprise server is here. Both Lisa and Homer send a packet to the enterprise server. What will happen to both of these packets with these rules? The poll should be open on Speak Up, so I invite you to give your answer. I wake up my Speak Up app. I close the poll. I try to close the poll. Bad performance of Speak Up today. Okay, let's close. Let's keep the close. Let's keep the poll formally open, but let's continue. The answer is the one given by the majority, which is E. So there are two flow rules. The first one has higher priority and is applied because Lisa matches 2, so the packets are forwarded to port 2. Since there is a match in the flow table, the IP forwarding table is not used. Packets from Homer match the second flow rule and are dropped, as you can imagine, because Homer is usually doing bad things. So you see that by adding the flow table, we have the combined effect that is described here. All traffic to b.d.star is killed, except if it's arriving on input 0. And the traffic that is not killed is forwarded to output 2. Traffic that goes to b.star and not to b.d.star doesn't match the flow table, so is forwarded to output 1. So this is the kind of construction you can make with flow rules. This is implemented typically by having a central controller that will download the flow rules into all the routers or the switches in a given network. So this requires that the routers and the switches have a program that's able to interact with a central controller, which is typically called a listener in the context of software-defined networking. So instead of writing those rules manually in each of those communication nodes, routers or switches, we write them in an app, in an application, or even better, we have an optimization program that will compute the rules based on some objective that we have and download them into all devices here. So this is, if you want, back to a more primitive way of controlling a network, where we say, instead of having a smart thing like Dijkstra, link state, and all that stuff, where the routes are computed by the routers themselves, we do it in a central operation, and we download the results in all of the routers. So this is typically done today in data centers, in large data centers, where the boxes here are switches. This is also done in cellular network, more recent version of cellular network, the recent 4G, and also in the 5G deployments, where the boxes here are routers here. And the motivation for that is to have more control, like we've explained before. In data centers, you want typically to manipulate your flows for all the reasons of security that I mentioned before, but also for performance and functions also, as some servers may be dedicated to some task here. In cellular networks, this is primarily for security. Now we have seen that we can, in some sense, avoid the smart method that is used in link state and use software-defined networking. Do we need both? That's the question of this poll. Okay, merci. Voilà, managed. I close the poll. And the majority says C, which is probably the correct answer, because you still need to be able to communicate from the central controllers to all the routers. So in order to communicate, which is typically done over a TCP connection, for example, router R4 needs to find a path for the central controller. So you still need a bootstrap method. You need a default method that will allow all the routers to communicate together. In some cases, for example, in some data centers, you may have a central communication system that allows to talk directly to the boxes, which in that case would be more probably switches than routers. You may have an Ethernet port on all of them that is connected to a big LAN that is used to control them. So in such cases, then you can do SDN only and not have a routing protocol. But that means essentially you are in a very local environment where all boxes are together, and you can talk to all boxes over a dedicated communication link. This is not typical. In general, you need to be able to communicate remotely, and so SDN will often come as a complement or as something that supersedes the default rules that are computed by OSPF. Voilà, that's what we will see, at least in the theory part, for OSPF. And that's the end of this module on link state. Our next topic is congestion control. Congestion control is one of the things that quasi-caused the collapse of the internet Fortunately, it happened when the internet was very small, therefore it was not lethal to the internet. Here I'm showing a picture that I took in Paris that illustrates exactly the problem that occurred in the internet when we did not do congestion control. This problem is that here is an intersection where everybody is blocking everyone. You have interblocking. The cars do not move, so those white cars are blocked by the red cars and the black cars that are trying to enter. So this is typical Paris chaotic intersections. And what happens here is that the throughput, if we think of this intersection as the equivalent of a router, the throughput of this router is quasi-zero, and it is quasi-zero precisely at a time where there is a lot of traffic. So we have a lot of traffic. We would like the capacity to be more than what we have, and the effect is exactly the opposite. The useful capacity of a switching system here is close to zero. This is a pattern called congestion collapse, and that occurs in every complex system. So this is what we will discuss now. The internet, in the way we know it today, was emerged when we went away from store and forward. That was done before that. So there was email and computer networks before the internet, but they were using the store and forward paradigm, as we have discussed the first day of the course. And then the separation of TCP and IP and the end-to-end principle and the principle of having IP packets that are datagrams was really the invention that was in fact already deployed in Europe in the C-Cloud network, but that one did not survive. But until the 90s, until 94, we can say, the internet was a confidential network. It was, so the throughputs that you had were kilobits per second. And in the fall of 86, there was a sudden congestion collapse. So here is a statement from Van Jacobson in a communication he did at SIGCOMM. The throughput went down from 32 kilobit per second to 40 bit per second. Of course, if today our throughput is 32 kilobit per second, we cannot do this Zoom session. There's not much we can do on the internet. We could send text messages. That's probably all we could reach with such a throughput. And if it goes down to 40 bits per second, then it's even worse, right? So this happened, and this happened in 86 because when the internet emerged, it was done in a very naive way where there was no thinking about congestion control. It's not because there was nobody knew about it at that time. It was the internet didn't care about it. They just did it. It worked until it collapsed. There were other networks like DECnet, company networks, that were working and had thoughts of the congestion control problem. Also, the store and forward problem used mechanisms to avoid congestion collapse, but the internet did not. It did not prevent it from succeeding, which is one of the mysteries in history. So what happened at that time? Well, let's illustrate a very small scenario, which is not very far from how the internet was in 86. Here I have two hosts, S1 and S2, that are sending traffic to two other hosts, D1 and D2, over a communication network. And here I'm showing the available capacities on this link. S1 is connected with a link of 100 kilobit per second. S2 by a much more powerful link, 1000 kilobit per second. The transit link here has 110 kilobit per second, and those are the values here. So the thickness of the lines illustrates the capacity of the link. Now, if S1 and S2 are greedy, that means if they send as much as they want, S1 will send at 100 kilobit per second and S2 at 1000 kilobit per second. This is exactly what happens if you do a network where there is no congestion control. You send at whatever your machine can, and here the machine can whatever the Ethernet interface or whatever communication interface that was at that time, probably more a modem line here, is able to give you. Now, if both do this, I'm assuming S1 is sending to D1 and S2 to D2. they come into a router whose output link is 10 times less than the aggregate input speed. So there will be losses here sooner or later. Of course, the router will do its best to avoid losses. It has buffers, so the queue will build up, but the queue, of course, has some finite capacity, and when the queue is full, packets will be dropped here. So there will be drops in packets here. Here, there can still be 110 kilobit per second, but here, uh, sorry, so there will be losses here. And the question is, what fraction of the traffic of C1 and C2 will reach their destination here? Here, to ask the question more correctly, I'm assuming that the dropping is proportional to submitted traffic. Dropping here, when the router has to send packets here, of course, it will queue them, and the mechanics of a queue are sometimes a bit complicated to analyze, but in general, or at least as a crude approximation, we can assume that the probability that the packet is dropped is proportional to the flow to the submitted traffic of this flow here. So here, for example, this is submitting 10 times less traffic than this one. But the proportion of packets that are lost here should be the same for both flows. If we accept this assumption, what will S1 be able to send to D1 here? At which rate will S1 be able to send? Of course, S1 will send at the rate of 100 kilobit per second, but there will be losses. For example, if we lose here 50% of the traffic of S1, that the rate that I would consider would be 50 kilobit per second. And we know from what we've discussed in the transport module that if a flow loses 50%, then its capacity, it can still send at 50% useful information. So even if we lose here 50%, there is still benefit from S1 of sending 100 kilobit per second and dropping 50%. Presumably S1 will repeat a lot of packets to achieve whatever goal it has, information transfer goal. So what does your computation give? I close in a few seconds. And the majority says 10 kilobit per second, answer A, which is the correct answer. Let's see why. I assume here that the dropping is proportional to traffic. That means it's fair. So what is the proportion of dropping here? We are sending 10 times more traffic than what goes out. So the dropping probability is 90%. So the ratio of accepted traffic is 10%. So here, the volume of S1 that makes it is 10. Out of the 100, we have only 10. Then what happens at the output here? At the output, well, we have an output queue that is used only by this flow, so there is no drop. So 10 will go out here. So that's the answer to the question. But the other interesting thing is also to see what happens to S2. S2 will drop here 90%, so we'll submit 100. But here on the output port, I can send only 10. So 90% of this 100 will be dropped again, and what will be sent is 10 again. So in this network, both sources send at 10 kilobit per second. In fact, the volume of traffic that they can send is 10 kilobit per second. So if they code things intelligently, they're able to send information at 10 kilobit per second. The capacity that this mode of operation gives to each of the source is 10 kilobit per second. But if you think about it, this is stupid. This is the cost of anarchy. This is because every source is greedy and compute its best response to what it sees. And what it sees is simply its link capacity here. But if we would have a global view of the network, well, we could see that S2 cannot send more than 10 anyhow because there is a bottleneck on the path here. So S2, there's no point that S2 sends more. So S2 should limit itself to sending at 10 kilobit per second. There's no way it gets more. But by limiting S2 to 10 kilobit per second, we allow S1 to receive 100 per second here. So a better allocation would be this. This is what we would like to reach in the internet. We would like that the sources are able, like S2, are able to refrain themselves for sending such that other sources can benefit from what they could obtain here. So first take-home message, if we simply let sources be greedy, send whatever they can based on their local information, this is inefficient. But let's see that it can be even much worse. So let's see this scenario here. The scenario is a bit more complex to explain, though it is still very academic and is a toy example. I'm assuming here a ring network. The network is a ring, and at every node of the ring, there is a source attached to it that sends traffic to a node that is 2 hops away. So this ring obviously is not using shortest path bridging, but perhaps something like OSPF or Trill, because all sources will go 2 hop away and all links of the ring will be used. And I'm assuming that the ring is perfectly symmetric. So at every node, there is the same thing. So at this node, there is also a source that goes 2 hop away, etc. So at every node, there is a source. All sources are at the same rate and all link capacities are the same. What happens in this network? What happens if the sources are greedy? Well, we see that on one link, there are 2 flows. There is the flow of this source, but this flow is also using the next link, which means that if we look at this source here, this link has the source I, but also the source I minus 1. So on a link, there are 2 sources. If every source sends at a rate which is less than C over 2, then on the link, the offered traffic is less than C. And in our simple model, if the traffic that is offered is less than the capacity of the link, there is no loss. In reality, there can still be losses due to randomness of when packets arrive, but they will be small. If we ignore this, we have that if lambda is less than C over 2, every flow will deliver exactly what it has input. So lambda second, which is the output, which is the useful throughput of every flow, is exactly equal to the input. But what happens if we go beyond? So C over 2 is the capacity. If every flow is below C over 2, the network is below its capacity. If we go above, what happens? Well, we can redo the computation that we did a minute ago. It's a minuscule amount, more complicated, but not much. We can do the same thing. We can compute the ratio on the link of the capacity of the link and the offered traffic. The offered traffic is the source lambda, but also what remains of the source at the previous hop. So I call lambda prime the fraction of traffic that is accepted. By symmetry is the same everywhere. So what wants to go in this link is the fresh traffic lambda, the transit traffic lambda prime. So the ratio of accepted traffic is this one, which means that lambda prime, this one here, is equal to lambda multiplied by this ratio. That gives me this equality here. At the second hop of a flow, I have the same thing. What wants to go into the second hop is lambda prime plus also another lambda of node I plus 1. So the lambda second is equal to the lambda prime multiplied by the same ratio here. So I have 2 equations. Lambda is my input. It's something that is given. I have 2 unknown, lambda prime and lambda second, so I can compute them. 2 equations, 2 unknown. There's some hope that that can be computed. That can be done. We obtain a quadratic equation that we can solve. And at the end, I'm skipping some of the details. We obtain this formula. This is the amount of traffic that will get out of this network here for every source when we are above capacity. And here I'm plotting the function that we obtain here. We see that this is this declining function here. Here, when we are below capacity, we saw that what gets out is what gets in. And we see that when we're above capacity, then things go down. Well, this is exactly congestion collapse. Congestion collapse means when we go beyond capacity, the usefulness of the complex system decreases. Here, the complex system is a network. The throughput of the network is less when the input is larger, so it's non-monotonic. Of course, this is bad because the investment we've made in the network is not used. We deliver here less than if we would be operating at this point. We could deliver a capacity C per flow if every source knew that it has to send at most C over 2. I said C, it's C over 2. So if every source knew, we could operate in this region and the network would be delivering more, but it's delivering less. Worse than that, if you're curious and you look at what is the asymptotic of this formula when lambda goes to infinity, you will see that the throughput is in 1 over lambda. So that means that if lambda goes to infinity, the throughput goes to 0. So the more you send, the worse it gets, and in the limit, the network becomes completely useless. So this is congestion collapse here. So the take-home message is, as the offered load increases, the total throughput decreases, and this is what had happened in the paper that I mentioned of 86 in the internet. Sources were trying to send a lot of traffic. We can analyze why in microscopic terms what happens. All sources are trying to send. There's considerable losses. So TCP, if the window is large because the bottleneck is the network, not the servers or the destination here. So if the servers are lightly loaded, they give a huge window. So TCP sees a lot of losses and retransmits the packets all the time. So there is retransmission of packets. Now, a large fraction of the retransmitted packets are dropped when they hit the network because they're competing with other packets. But those packets that are dropped, a large fraction of them will not make it to the next link because they will be dropped again. So we serve some traffic that will not make it to the end. So we use resources of the network to give the resources to some packets that will not make it to the end. They will be killed before they reach destination. So this is why with a fixed capacity C, everything is as if the capacity had been reduced because the capacity is allocated to packets that will eventually die. So this is congestion collapse. This is another fun illustration of congestion collapse that can happen in road traffic. So any complex system, interconnected computer systems, the internet, communication networks, road systems, any complex systems is susceptible to congestion collapse. And the pattern occurs where when the system goes above capacity, then the system starts using more and more resources that are not dedicated to making useful work. So we should avoid this. How can we avoid this? That's the question. So a network should be organized so as to avoid inefficiency and in the worst case, congestion collapse here. So we would like to be maximally efficient. For example, use C over 2 in the network we gave. But let's see that it cannot be as simple as that. So here is a network with 2 links, a link at 10 megabit per second, a link at 2 links at 10 megabit per second each, and a number of flows. There is one flow 0 that goes end to end, a flow 1 that goes on the first link only, and 9 flows of type 2 that use only the second link here. If we want to maximize the throughput, that means maximizing the total rate that goes out of the network. That is the sum of x0, x1, and 9 times x2. What is the maximum value that you would compute for this network? close in a few seconds. Well, the intuition says B, but the correct answer is C. In fact, if we really care only about the total throughput of this network, the sum of x0 plus x1 plus x9, then the optimal is to give 0 to x0 here, and to give 10 to this guy, and to share the 10 with the 9 guys here. So we'll have 10 to the blue, 10 in total for the greens, so total throughput will be 20. Here. It's easy to see that you cannot do more than that, because x0 plus x1 is less than 10 and 9x2 is less than 10. So total capacity is 10 plus 10, 20. So you cannot do more than that, but you can do this. So the answer is 20 megabit per second. Okay, but the interesting thing is now what happens to x0 when we reach the maximum throughput. So assume I know there is at least one allocation that gives 20 in maximum. For any allocation that reaches the maximum throughput, what do we have for x0? I close the poll. And the majority says none of the proposed solutions, which is correct here. If we assume by some allocation we manage to get 20 in total, that means we have this constraint into the rate. And we want to find all values of x0, x1, x2 that satisfy this. Then by looking at the various constraints we have here, we see that we must have this inequality that must be an equality, and therefore x0 must be 0. So the only way we can reach the maximum throughput of this network is by shutting down the red flow here. Well, this is our first take-home message. When we decide how we run a network, what criterion should we use to decide what is the optimal rule that we should apply to do congestion control? It cannot be to maximize the total throughput. Would have been nice, then things would have been simple, but it cannot be. So this relates to an important concept in networking, but also in other domains, called Pareto Efficiency. So we cannot simply look for the allocation of rates that will be giving the maximum sum, because it's probably not something we would like. You don't want to run your network such that x0 is completely shut down. But you still want it to be efficient under the concept of Pareto efficiency. So we say that an allocation of rates is Pareto efficient if it cannot be improved unilaterally. Improved unilaterally would mean that if something is not Pareto efficient, if I can improve what I give to one source without impacting any other source here. So this is at the minimum what we should have. It's easy to see that this is equivalent to saying that every source has a bottleneck link. So a bottleneck link means a source such that it uses one of the resources where a constraint is satisfied with equality. So here, a source is that uses a link which is saturated. For example, if I look at this allocation, this was the allocation that we found that maximizes the total rate, the sum of the total throughput of the network. We give 0 to flow 0, we give 10 to the blue flow, and we give 10 to the 9 green flows all in total. So the same 10 over 9 to each, right? So is this Pareto efficient? Well, we ask, is it possible to increase the rate of one source without changing the others? Well, if I try to increase the rate of the red, I will need to decrease the blue because here there is equality. If I want to increase the rate of the blue, then it's impossible. If I want to increase the red of one of the green, I need to decrease the red of another green here. Or another way to see it is that sources 1 and 0 have a bottleneck because on their path for the red and for the blue, this link is saturated. So they have link 1 as a bottleneck, and link 2 have the sources, the green sources have link 2 as a bottleneck. So every source has a bottleneck, so it is Pareto efficient. So the throughput maximizing allocation is always Pareto efficient, but obviously this is not the one we would like to have. Indeed, there may be multiple Pareto efficient allocations here. Here I'm giving another example, again with one red flow, one blue, one green, and one black flows, and there are 3 links with the capacities that are given here. Which allocations are Pareto efficient? This is a bit more involved than the usual poll, so we might take 1 or 2 minutes to solve it. I close the poll in a few seconds. Ta-da. And the correct solution is F, which is the majority vote. Let's see why. So let's look at the first allocation here. To make the thing more readable, I've written the values of this first allocation. Of course, the red flow has the same red everywhere, but I wrote it repeatedly to analyze more easily. So the one way to see if it's Pareto efficient is to see if every source has a bottleneck link. So we see that the red here is using this link. The blue is using this link only, and this link is not saturated because there's 1.5 here. So the blue is not saturated, so this is not Pareto efficient. In fact, I could increase the rate of the blue to 1 or to any value between 0.5 and 1. That would not change anything to the others. So this is not Pareto efficient because I can increase the rate of X1 without touching the others here. In contrast, allocation B, if we do the same calculation, B has 1, 1 here. So the blue has a bottleneck link. The red also has a bottleneck link. The green, 8 plus 1 gives 9, also has a bottleneck link. And the black also has a bottleneck link because we have 10 here. So every source has a bottleneck link. This is an example of a Pareto efficient allocation here. Allocation C, which is different from the previous, has the same property here. We see that the red flow has a bottleneck link, which is the first link. The blue flow also. The green flow has a bottleneck link, which is not the first link, but not the second link, but the third link, because it's sharing this link with the red and the black, and here the capacity is reached here. So not all links are saturated, but every source has a saturated link on its path, so it is Pareto efficient. It cannot be It cannot be unilaterally increased here. So we see on this example that there can typically be multiple Pareto efficient allocations. So maximal efficiency, which is what we want in a network, we want to avoid congestion collapse, we want to use the network efficiently, but it's not clear what goal we should have. We should be Pareto efficient, certainly, but there are many Pareto efficient allocations. We've seen that the throughput maximizing allocation is one, and it's completely unfair. And we've seen on other examples that there can be multiple allocations in general here. So the question is, among all the Pareto efficient allocations, which ones are fair? And this is what we would like to do in the internet. But for that, we will need to discuss what is fairness. And this is what we will do after the break. So we stop now for 14 minutes until 1:15.